Before we continue with law of large numbers and the behavior of random variables, another terminology for law of large numbers is asymptotic distribution of random variables, or limit theorems, or limit behaviors, or there is graduate courses in some math departments and other places. It's called random matrix theory if you deal with eigenvalues and of matrices. So we like to introduce another important concept, which is ergodicity. So ergodicity is a very simple and useful definition that we'll need it. So ergodicity means that quite often you have a random sequence, because your random sequence you have for x of n, you have a mean for your random variable. Let's say it is equal to mu, and also this is a statistical mean, which is equal to integral of x, and then the distribution of x of n x dx over x from minus infinity to plus infinity. So this is using probability measures, so the expected value. This is a statistical averaging, but you could have a temporal averaging. Temporal averaging means that you take samples of this random sequence, you say x1 plus x2 plus xn, and then divide it by n, and we call it x bar n. So this is temporal averaging. So the first one is the averaging over distribution. So average over distribution. So here we average over time over different samples. So this guy is a random variable, because the sum of random variables is a random variable divided by n remains random variables. But this guy is a real number. In this chapter, we have learned convergence. So if this temporal mean, which is a random variable, if this guy converges to a statistical average, if converges, we call it ergodic. This is a general definition of ergodicity. But for ergodicity, you need a mode of convergence. For example, we say that a random process, x of n, is mean ergodic. So as soon as we say mean ergodic, we consider two different averaging. One is going to be a temporal averaging, and the other one is going to be a statistical averaging, which is going to be this one. If these two guys, they converge to each other, we call it mean ergodic. But for convergence, we need a mode of convergence. For instance, here in this example, you say mean square sense in the mean square sense. So anytime you see ergodicity, you need to define what is statistic. Here the statistic is the expected value, and then you take the similar averaging, temporal averaging for it, and then you choose a mode of convergence. Here I selected mean square sense. If it's sample mean or temporal mean, sample mean or temporal mean, or sample mean. If you're dealing with time, you say sample mean. If you're dealing with images, you could say a spatial, or if you do averaging over a space or a location, so again you could have you could define ergodicity as well. So in that case, you say ergodic in time or ergodic in the space. If these two means, they converge together in the mean square sense, which is to say that the distance between the sample mean and expected value, the mean square error, converges to 0 as n tends to infinity, where mu is the sample. So this definition is complete by itself. But remember that when you define ergodicity in other senses or in other statistics, For instance, I could say the random process is power ergodic. If I say x of n is power ergodic, then I have to consider mean of power of my random variable, mean of x of n to the power of 2, which is equal to integral of x to the power of 2, the PDF of x of n x dx from minus infinity to plus infinity. So let's say I call these p, and then I have to consider the temporal averaging. I have to say x1 to the power of 2 plus x2 to the power of 2 plus etc. plus xn to the power of 2, and then divided by n, and let's say this is like a random variable, I say zn. Okay, so if limit of zn minus p, let's say to the power of, here I put, instead of mean square I put L1, if this becomes equal to 0 when n goes to 0 and n goes to plus infinity, then I say that x of n is power ergodic in L1 sense. If you put 2 here, it becomes in mean square sense.